Just a second. Okay, I think we're good. So, hello everyone. Marco, I don't see your screen anymore.
I can see it. Oh, now it went away.
Sorry, now is me that I remove it. Can you see it now?
Can you see it, Andrew?
I cannot, but I can still see it when you.
Okay, let me retry.
I have no. Now I can. There we go.
Yeah.
Great. Okay, so we can start. Welcome everyone to the fourth episode of our privacy tech talk series. Today we are honored to have Marco Gaboardi, professor of computer science at Boston University. Marco is internationally well known for bringing programming language techniques and expertise and formal verification to differential privacy, helping developers write data-driven software that is both provably correct and practically usable and private. So the trio. The talk will be followed by a Q&A session chaired by Andrew. We are excited for the talk. Marco, you have the floor.
Thank you. Thank you very much. Thank you for the invitation to give this talk. It's an honor to be here. So today I was planning on talking about something that I have been working on in the last 15 years, which are programming and verification framework for differential privacy. But before starting, I want to give you a bit background on who I am. So I actually started with my PhD in computer science in Italy and France with working on logics for reasoning about computational complexity. And I just got to differential privacy basically during my postdoc when I was at the University of Pennsylvania. At the same time I was there, basically Ron Roth, who was before in this tech series, just joined the faculty, and so there was a lot of interest in...
Just a second, I think we're still having a problem with the slide sharing. Can you start again and reshare your screen? I think somebody messaged me that there is still an issue, so I will.
All right.
Give me 1 second. Sorry.
Let me try to share only the app this time. Can you see it now?
Yes, let me double check that we can see it on the stream as well.
And I try to...
I think it's perfect. No, I think
okay. All right. Let me get back to this. So I started to work on programming languages for differential privacy when I was a postdoc, and this took a lot of the rest of my time in the subsequent year. But I want to highlight a few things that really influence my research and the way I think about differential privacy. In 2015, I had the opportunity to visit Harvard Circus Center and work on the Privacy Tool project, where, as the word says, the goal was to develop a tool for privacy, in particular differential privacy. I know that Salil Badan already was also presenting during this series, and also Kobi Nissim, and they were also there in 2015. Kobe was also visiting at the same time. And so I had a great opportunity to learn more from people that develop differential privacy as a notion, not from the programming language perspective. And this was also followed by a privacy semester at the Simon Institute, where again I had the opportunity to see the broader picture of privacy, not only through my research, but the different angle that privacy brings. And another thing that I think influenced me a lot is that from 2012, 20, I started to be more involved in actual development of differential privacy, in part through the OpenDP library design, of which I was an active member, and also I co-founded the company, DeepL AB, which try to bring differential privacy to people that need it. So I had the opportunity to play a bit more in the practical term with differential privacy. But today, what I want to give you is a perspective on programming framework and verification framework. And the way I think about this is that about these tools is that they are tools that help when we want to go from an idea to an implementation in making the process mathematically rigorous. So it's about helping, guaranteeing that the application we build are correct. This is the main goal of those tools from my perspective. Now, we may wonder why correctness matter. Correctness matter because when we give it up, bad thing can happen. There are plenty of examples in the computer science literature, real world literature, where bugs in software, software that was not working as it was designed to work, created big trouble, from a rocket that exploded to a car that had accident to entire system that fell apart. Now, using this programming framework and this verification framework, we can help to bring more correctness to our application. Now, one of the problems with today's environment is that the notion of correctness is changing. Correctness 30 years ago, correctness for software 30 years ago was easier to define, or at least there was a perception that was easier to define. Today, correctness is a bit more difficult to reason about because there is an uncertainty. Most of the applications we consider have some form of uncertainty. Most of them come from the data or from the process, and this makes the notion of correctness more difficult to nail down. But in our case, we are lucky, we have one clear notion of correctness, which is relatively complex, but is clear at least. And is our program differentially private. So most of what I will discuss today is about this question. Can we guarantee that our program are differentially private? Now, this is not the only notion of correctness that I think is important to keep in mind in this setting. There is another one, which is our program useful? Because when we look at differential privacy, we are changing a bit the way our program behaves, and so we want to still understand if it is useful. But in this talk, I will mostly focus on the first kind of correctness. Also, another thing that I should say is that in this talk, I will focus mostly on programs. So correctness can be defined for programs, of course, but can also be defined for systems. And the technique to reason about correctness for systems are different from the technique to discuss correctness for programs. There is a large research literature in both directions, but in my talk, I will mostly focus on programs. So I said that bad things can happen when we don't think carefully about correctness, and so we may wonder how things can go wrong in differential privacy. And I want to bring a few examples that I hope they explain why correctness is not a trivial concept for differential privacy. So the first example is a relatively simple algorithm that we will also discuss later in the talk that is called the sparse vector technique. This is an algorithm for differential privacy that was introduced by several people already 15 years ago, 10, 15 years ago. The problem is that several people tried to do variants of this technique, and you see now on the screen 6 different variants that people have looked into. Unfortunately, many of these variants are not differentially private. 2 of them are differentially private, and 1 is almost differentially private. So even when we look at algorithms proposed by experts in the field that have just 9 lines, like this example, it's difficult to say if they are correct or not. They were proposed because the author thought that they were correct, but actually they were not. And so it's subtle for, if we want to use differential privacy, to be able to tell whether our algorithms are correct or not. Another issue that we find in differential privacy, we know this already from 2012, but even before, is that we need to represent the technique of differential privacy on finite computer, and when we do this, we need to be careful. We know this, of course, from other areas. It's not only the case of differential privacy. Cryptography is another example. Security is another example, where we need to be careful on how we make our data type finite and how we make our computation finite. And we know that if we don't do this in the right way, we can have attacks that basically destroy the guarantee we are trying to provide. Here I put one of the seminal paper in this area, which is an attack based on irregularities of floating point implementation for a basic mechanism of differential privacy, which is the Laplace mechanism, that show basically that just by using irregularities of floating point, we can reconstruct the secret that we are trying to protect. And another kind of example still on floating point, this specific one, but also in general is a bit more general phenomenon. We also may have other kind of attacks, like side channel attacks, timing attack, that we can get just by observing some running time of operation, or of there was a subsequent work about sampling scheme, and so on. So in particular, we can have a lot of attacks just by the computational model we are looking at. So for all these reasons, I think it's important to focus on correctness in this setting. And there are 2 ways I want to talk about on how to show correctness. One is by designing a programming framework which guarantees that our components are differentially private by design. And this is something that has engaged the programming language community for many years. So I want to tell you a bit more about this. And the second instead is more on the formal verification part of my talk, which is we can formally verify some component to be differentially private. I will discuss both of these approaches talk a bit about the motivation and also talk about some recent important development in both directions. Now, when we talk about correctness and we talk about technique to guarantee correctness, we need to keep in mind some trade-off. I put some of these trade-off here. They are probably not the only one we have, but three directions that I think is important to keep in mind. One is the usability of the technique that we design, because we can make very sophisticated technique, but then that only very few experts can use. Or we can choose to do less sophisticated technique that everybody can use, but maybe have other trade-off in the other direction, which two important directions are expressivity in terms of the complexity of the program that we can capture. So how many examples, in concrete terms, how many examples we can capture. And the other that I think is important to keep in mind is the strength of the correctness guarantee. So correctness in reality is not just a 0-1 concept. It's more like a continuum. We can guarantee some form of correctness, but maybe is not complete correctness. For example, we can show our application to be correct in the sense that it provides differential privacy, but then maybe as a side channel attack. And this is a kind of strength of the guarantee we want to provide. So I will not fill in, I will not put the tool that I will present on this map, but I want you to have this map in your mind so that you can think about the different trade-offs we have here. But now let's turn to differential privacy. So I assume that this community has an understanding of differential privacy. I know that also before me, there were other tech talk about differential privacy, so I will not focus too much on the motivation that have brought to the design of differential privacy, but more on how we can design programs that are differentially private. How can we achieve differential privacy? So the idea on how we can achieve differential privacy is pretty simple. I think even in the news you can tell it easily. The idea is to add some noise to the result of computation on some data. The idea is that we can use this noise to protect the data of individuals. And if the noise is not too much, we can still learn something useful from our analysis. So this is the basic idea of differential privacy. But to understand it a bit more in detail, we need to look at how this idea can be actually formulated as a definition. And actually, when we look at the definition that I put now on the screen, it's not exactly like the intuition I gave you before, but has different components that are actually quite difficult to grasp if you are not used to this kind of definition. So let me try to highlight some of these components. So what we are interested into are probabilistic queries or a probabilistic function. So you can think about our function with some noise. And we can say that this function is differentially private if when we look at two data sets, sorry, let me move my animation. When we look at two data sets that differ in the data of one individual, we can guarantee the equation you see here. The form of the equation is not very important here. We basically are asking that the probability distribution that define the function we are looking at on the data set that differ for one individual are similar. This is what we are interested in. But the component here that make reasoning about differential privacy challenging is that we are talking about probabilities. And we know that talking about probabilities can be tricky because probabilistic processes are more complex the non-probabilistic one. And also, we are talking about some quantity. We need to guarantee some bound of some form. And finally, we need to, the definition as it is given, we are reasoning about two potential situations. In this case, two potential data sets that differ in one individual. So we have this kind of two hypothetical situations that make the reasoning a bit more complex. Now, my claim is that to reason about this in the right way, we need some tool so that we can deal with all these challenges. Now, if you are an expert in some area like cryptography, you may know that this definition is not the unique case where these three challenges arise. Actually, we find many similar definitions in cryptography. And not surprisingly, some of the tools I will present later actually come from cryptography. Some ideas come from the verification or the reasoning about cryptography. Now, let me focus on the first approach, which is designing a programming framework for differential privacy, which guarantee differential privacy by design. To do this, differential privacy offers some important properties that are useful for this design. One is a sequential composition, is one of the properties that probably made differential privacy quite famous, and is the idea that basically if we have multiple analyses that we are performing on our data set and we add noise to each one of them to guarantee differential privacy, then we can think that the overall process is differentially private. Now, what we need to keep in mind is that in this case, if we don't know anything about the data and anything about the query, we need to sum up the quantity of differential privacy. So if we start with epsilon differentially private query and we run n of them, then we have an epsilon differentially private process. This is not the only form of composition. There are other compositions like a parallel form of composition where we can split our data and then perform analysis on each of the resulting pieces, and then guarantee that the process is still differentially private without actually blowing up the parameter. Now, what this kind of composition gives us is a way to reason about differentially private programs using a concept of privacy as budget. So we can think about, we have a budget of privacy, which is this parameter of the definition of differential privacy epsilon. And then we can guarantee that some basic component will use some of this budget, and we just need to account for the overall budget. This is a good way to start because basically it allows us to get away with limited reasoning about probability, and can also be reused for other form of composition. Now, I want to give you an example of, I want to actually use an example to lead a bit the discussion of how we can design a programming framework around this. My running example is a CDF, where we are interested in providing the CDF, which is the number of record with value less than X, for a bunch of input data, values that we can consider are some kind of beans of our CDF. So in my example here, for instance, I want to compute CDF of 20, 30, 50, and so on. Now, if I do it in a non-private way, I can write some simple code like this. This is a couple of lines of code. Is in a language that, let's say, is a kind of database language where we can we have our database and we can process it through some transformation like where here in my for loop. So I count basically the values in my in my data set that are less than the bucket at index I, and then I count. Sorry, I select them and then I count them. It's not very important, the precise code, but is how we could write it in a non-private way. Now, if we want differential privacy, we could add noise to each of the result in the list in the output list, and use our sequential composition to guarantee basically differential privacy. So in particular, I could add the noise proportional to my budget epsilon over the number of buckets I will use. This is what K represents in this slide. So in concrete code, basically, I can just change what I wrote before to add a small part where I add the noise proportional to epsilon over the length of the bucket list. So by sequential composition, I sum up these for length of bucket and I get my epsilon. So this is what we could do, but I did this manually. Now, how can we do a programming language that support this design? Actually, this it has already been done, and I will take as an example Pink, which is the first language for differential privacy, which Frank McSherry, one of the inventor of differential privacy, proposed already in 2008. And this base is called the Pink because it's based on Link, which is a library for queries in C#. And they basically implement a bit the idea of privacy budget in the sense that we have a runtime monitor that keep track of the privacy budget, and we have some basic analysis and some basic transformation that use this budget. So how our example look in Pink look like this. So you can see some similarity with my code from before, but now we have some additional command, and I will walk you through that. So in particular, we have an agent which basically we can create to manage the budget. This is the runtime monitor that can look for the consumption of the budget. And then we can basically associate the database with this agent, so that the agent will keep monitoring the privacy budget for this specific dataset. And then when we process this data set, we have a transformation like the where that I mentioned before. And so this is a select basically of all the values that are less than a bucket at index I. And then we have aggregate operations. And this aggregate operation in particular is a noisy version of counting where we give our privacy parameter that I mentioned before. Now, this is the way we can program in Pink, but I want also to look a bit inside these boxes to tell you a bit about the architecture of Pink, not only what we can do. So when we look at transformation, like the where command that I showed you before, actually this is very similar to the Pink, to the link method. In fact, it's just a wrapper around the link method where we have the same where condition, but basically we add some information so that we can guarantee that we are still working with this Pink variable, which are these data set wrap with an agent. And we create a new one here. But also we take care of the stability, which is something important for differential privacy, because we want to see how much a transformation is affected by the change of one individual. And this is the key to guarantee differential privacy, because we want to add a noise that is proportional to how much an individual can affect the result. Now, this, as I said, is inside the design of Pink. And here is the other component, the aggregation. Is the noisy count. Here, basically, we need to check if we have enough budget. Now, this epsilon is, of course, a local epsilon that is bound on the parameter of the function. But we need to check if we have enough, if the agent has enough budget to run our query. Otherwise, we will not give a result. And we can add the noise. Here is the Laplace distribution, but it's not important for this talk. Now, what I want to do is to unfold further this code, because what is really going on is that we are computing the sensitivity, which is, again, how much an individual can affect the result of the query. And we can check if we have more than this budget, and then we can add the noise as needed, and we can decrease our budget. So this is the accounting we need to do in order to guarantee differential privacy. And once again, this is done basically by the API. Now, this mostly conclude my code for today. I will not show more code to you, not much more code, but I wanted to show you some code to understand the design of this programming framework, because it's led the design of many other programming framework afterwards. And actually, we should ask ourselves, why aren't we done with this? So what are the issues that remain? Here I identified some issues that people have tried to address after Pink. So this will motivate a bit some of the work I present after. I will not, just a disclaimer, I will not present all the programming framework. It would just be out of I would run out of time very quickly, because there are many programming frameworks that have been designed. So it will be a bit of a partial view, based in part on what I have worked on, but also try to highlight some of the ideas that a community has worked on. So in this respect, also this issue, you should take them as not a conclusive list, but more as a list of some issue that has motivated more research. So the first, I think, is the first issue is that several aspects of the enforcement depend on particular choices. In particular, I unwrap some of the code to show you there were some points where Sherry, that has designed Pink, has to take some decision about stability and sensitivity constant, and how to design noise mechanism and so on, but also how to do the accounting. And this was built in the design of Pink. Also, I didn't show you, but when one needs to add more complex algorithm, basically they become black boxes. So we cannot program them directly in Pink. And finally, Pink doesn't really tell us much about the accuracy of our program. And so people have looking now to also talk about accuracy. So to address some of these problems, I will present a few work that have contributed to this. So the first that I want to mention is a series of work that started around 2010 at the University of Pennsylvania around the language that is called informally FADS, which is a language for differential privacy based on a slightly different perspective than Pink on reasoning about sensitivity rather than exactly composition, but we know that the two are related. Is a compositional reasoning about sensitivity, I should say. And the enforcement, instead of being dynamic, like in the case of Pink, is static. So in particular, the FADS language and all its variant were focusing on using type checking as a way to guarantee differential privacy. So if the program type check, then is differentially private. And also, it was developed around a formal model based on metric spaces and non-expansive function that guarantee the correctness of the constant we use when we look at stability and sensitivity. To contradict myself, I may show you again some code, but is just one line of code here, just to show you how a query in FADS would look like. Is a functional language with some keyword. But the key point that I want to highlight is that when we do the type checking, there is some information that you can see between the square bracket. In this case is a 1. That is the sensitivity of this function. And this function is a compose function. And so the type checker will check that this 1 is correct. And this increase a bit the reliability of the programming, because we don't have to leave everything to the user or to the API designer, but we can have some of the tool like type checker do some work for us. This series of work has been extended in many directions. Basically, I would say that the basic idea is to do static checking through types of this series of work has been extended to address a more advanced algorithm, to support different notion of differential privacy, to leverage static checking of ambient languages, in this case of Haskell. And I have contributed to some of these. I highlight the one I contributed with my research. I think this line of work has influenced some of the design choice of other programming framework. And so, although fuzzy is not used itself nowadays, it has influenced a bit how we think about programming framework for differential privacy. Another example that I want to bring is the OpenDP framework. I will not spend too much on this because there was already a talk by Salil Badan that has focused more on this, because he is the one leading this community effort at Harvard University. And a key component of the OpenDP framework is a library with a privacy model that is similar to Pink, in the sense that is focusing on composition, but is much more elaborated in the sense that it supports different privacy notion. It supports interactive model of computation. In particular, it supports them as a first-class object. So what do I mean by this? If you remember my example of Pink, I show you how the budgeter was basically built in the API. While in the OpenDP library, we decided, I was part of the design committee here, we decided that the budgeting or any way to interactively work with this agent or with this queryable is a first-class object that can be implemented directly in the OpenDP library. Another important aspect of this effort is the community-based vetting and validation of the different components. We were lucky to have some people volunteer, included Tudor, volunteer to help us with doing vetting of the components. And this bring the reliability at a different levels. Another, here I also do a shout out for my company, but I think it also is because it has some interesting design choices. And actually the design choices came from our research. So in Dipella, which is a company that I co-founded, and but is also the name of our language in some of our research paper, we designed a DSL that not only guarantee privacy, but also allow one to explore the privacy utility trade-off. And we do this by basically having an accuracy model based on primitives and composition. So we show that we can reason compositionally also about accuracy, and we can check them statically. In this effort, we use a lot of static analysis technique to improve the usability and to basically let user provide less, to remove a bit the burden from the user and to guarantee correctness. So these were three different directions that people have worked on to extend the pink model. But they didn't address all the issues I mentioned before. So in particular, the more complex algorithm in all these frameworks are still black boxes. And also it's difficult to reason in these programming languages about the noise mechanism implementation. So you just assume that you have a noise mechanism implementation. To address this issue, basically is where formal verification come into the picture. So we can think about formally verifying that some of these components that we should think about black box in the programming framework are actually, we can verify them to be differentially private. Now, here is my one slide introduction to the idea of formal verification. Is an idea that actually already Alan Turing had in the 40s, is basically is trying to answer this question: how can one check a routine to make sure that it is correct? And the basic idea that Alan Turing and many people after him work on is to break down the program in a small component and check the small component with some assertion that we know is correct, and we can check individually and then guarantee the correctness of the whole program together. Now, the only thing that maybe Alan Turing got a bit wrong is that he was focusing on a man to do this checking, while today we think more about a man and the machine. So we can have machine check this for us. And I will present a couple of approaches also in this direction. So one approach is the approach that is based on the idea of program logics, which are logic to reason about programs, that we can use basically to reason formally about program through a specification that is given in terms of precondition and postcondition. So we are interested in what result the program can compute under, and this is the postcondition, under some assumption that we have on the input, which is the precondition. And the interesting part, like we saw before, is that we can design some logic that has rules that prescribe the correctness of the whole program with respect, based on the correctness of the single rule. So we can think about rules as something that talks about a single command, and we can prove them correct, and then the correctness of the overall program follows. Now, as I said, we think about this as done in a way by man and machine. In particular, we think about the verification tool as something where we provide our program and some annotation, and then we have a verification tool that check that the program is correct with respect to our annotation. And to do this, we can use a lot of decision procedure solver, interactive tool. In particular, in the large family of solver, one particular class of solver is used a lot in verification are satisfiability modulo theories, where we can also basically use a part of our program in the logic directly. Like here, you see that you can talk about variables and about what the variable contain and so on. Now, can we use this to reason about complex algorithm? Here is a candidate that I already mentioned before, the sparse vector technique. As I said, this is a relatively complex component, and usually we cannot just reason about this in our programming framework. We need to reason about this as a black box. We need to have some proof about it and then integrate in our framework. This is something that the community effort that I mentioned before, for instance, from OpenDP, would need people to do it for us. But it turned out actually that we can reason about this through some verification tools. So let me talk 1 second about what this sparse vector do, so that we understand that maybe I will try to convey the idea of the challenge that it poses. So sparse vector is the idea that we have a bunch of queries, let's call them Q1 and Qn, and we have some threshold T, and we want to answer basically the queries that are above the threshold with some answer, and the queries that are below this threshold just we don't want to answer. We can just return some default value bottom, and we want to keep doing this. Okay, and we want to do this in a way that we get some epsilon differential privacy, but in particular, we want to pay some part of our privacy budget only for the queries that are above the threshold. Basically, we don't want to pay for the queries that are below the threshold. And actually, we can think about a simple subcomponent of sparse vector, which is just telling us if one query is above the threshold, and we can stop when we find the first query that is above the threshold. And we want now to return the index of this query, but in particular, we want to do it in a way that we don't pay, in a way that we don't pay for all these queries that are below the threshold. Now, if we think about composition, like I presented you before, we see that basically for each query, we would pay some budget. And so very quickly, we would end up with K times epsilon differentially private algorithm. Sorry, this should be K, not N. In reality, what we can do with a more advanced analysis is to show that this is actually just epsilon differentially private. So in particular, we pay only for this last query, and it doesn't depend on the number of queries. Now, in reality, the intuition is that we are using some part of our uncertainty to pay for all the queries that go under the threshold, and part of it for the query that goes above the threshold. But overall, the important point is that we don't pay, it's not like in composition where we accumulate for each query some part of the budget. We can pay for all of them at once. And to achieve this, the algorithm, basically what it does is what you would expect. So just try to run all the queries, but basically add noise not only to the queries, but also to the threshold. And the noise on the threshold is key to have this behavior. Even if we think about the threshold as some public information, this is still a key component to add noise to the threshold. So can we use our approach to verify this example? Now, there is some challenge actually. So the first challenge is that the verification tool I mentioned to you before use logical formulas, while here we are interested in a probabilistic property. And we could try to use some solver that use probabilities, but this maybe is not at the moment is not a scalable approach, because reasoning explicitly about probability is very complex. And so we would like instead to avoid again reasoning about probabilities as much as possible, and just keep reasoning about logical formulas without a reference to probabilities. The second challenge is that when you look at the privacy proof for this kind of component, they are quite complex. Here I report the above threshold proof, that an example of the above threshold proof. And it's difficult to distill the main idea that we could use for the verification. Now, in a series of work with some collaborators, we actually realized that an interesting ideas that solve these two challenges is to use a concept that comes from reasoning about probability, which is called the probabilistic coupling, which is the idea of putting two random variables on the same space and adjusting a bit to reason about differential privacy. In particular, we can have a logical formula, which is what we use to really reason about, to do the verification, which talk about ways we could couple the two random variables. For us, the random variable here are the noise that we add. So in two different, in two run of the algorithm on two different databases that differ for one individual. So we can have a logical formula to describe how we couple them. And then we can use divergences to measure how much we get as an approximation. Now, the idea of this approximate probabilistic coupling is complicated, and I don't want to go in the details with this. But what I want to convey the main intuition, which is basically a tool to be able, when we reason about a program, to think about how two different execution of the program would go probabilistically in the same control flow. So we want to reason for above threshold in what is the probability that we get the same sequence of holes representing below the threshold and then true. And we can do this basically through this approximate probabilistic coupling. And we can implement this in a tool that we have implemented this in a tool that is called EasyCrypt, which was designed originally for reasoning about cryptography. Again, is a tool that has the same structure I mentioned before, backed by SMT solver. And again, the key point is here, there is no need of probabilities, but just a logical formula and some accounting, but is a way of reasoning that is more involved than the one we have in programming framework. Now, this work is not the only one in this direction. Another work has used a different concept that is called the randomness assignment, and this has been implemented in several tools that actually have a lot more automation than the tool I mentioned before, and they require very limited annotation. For example, sparse vector can be verified with just 2 lines of annotation. And there was more work in try to support fully automation, and there are tools that can verify completely example like sparse vector. So we just say what is the level of privacy we want to achieve, and the tool completely verify this for us. Ideas similar to the one I presented here have also been used to finding counterexample, something I don't have time to discuss too much here about, but there is a lot of literature in try to help a developer to find counterexample to differential privacy, specifically to differential privacy. So it's a bit different from general counterexample generation. There is, I realized that because of the technical problem and because I'm going a bit longer, I have one more idea I want to present, so I will go a bit fast on it and then conclude. So another example of a challenge I mentioned before is reasoning about floating point implementation. And now for this, it cannot be done really with the tool I presented so far, neither programming framework nor program logic. So one approach we can use is the approach of proof assistance. I don't want to go too much into this. Proof assistant are tools like the one I show here, where one can basically prove, assisted by the computer, different lemmas and theorem also about program. These tools have been used to verify a result in mathematics, like the four-color theorem or the Kepler conjecture. But for us, it's important that have also been used a lot for the verification of software, in particular for cryptography and for protocol and compiler and operating system. And there are some work that try to use a proof assistant to basically implement a finite version of differentially private mechanism and guarantee them correct. This kind of reasoning is more complex, so it requires some knowledge about proof assistant. Not everybody can use them, but it is very powerful. One work that I want to mention is very recent. It is presented actually this week at a conference in Korea, is the work by a team at Amazon on the SAMPSERT effort, which is a verified implementation of the discrete Gaussian sampler. So is aligned with what I mentioned before. So they verify the discrete implementation of Gaussian, which is very important in differential privacy, and which this verified implementation has already found use in some of the services that AWS provide. Again, it's not something that everybody can do. Amazon has a great team working on formal methods, so they were able to do this thanks to their strength, but is a considerable effort. But I think what it shows is that we are close to have this kind of technique employed directly in industry. And with this, I want to basically sum up. What I try to provide today is that the properties of differential privacy can be leveraged to design programming and verification framework, and that there has been a lot of research in the last 15 years on it. Some development are actually mature now to see employment in industry, like the one I just presented, but also the OpenDP effort, and also there are several companies, not only the one we created, that are using some of this tool in industrial application. I want to conclude with a personal note. In this journey through the work on programming and verification framework of differential privacy was great for me, because it was a great opportunity for interdisciplinary collaboration. I'm a programming language person by background. Even just learning about differential privacy was going out of my comfort zone. And I did it, and I learned a lot by collaborator. And also, it was a great occasion to see application of this kind of formal research, as I just mentioned. And then also an occasion to getting some exposure to interaction with the larger public, because it's not only about our work, but is what we bring to other people in terms of differential privacy. And this mostly was from my research, but also from my more business related role. And with this, I want to conclude. And I thank you, everybody, for listening.
Thank you, Marco, for the great talk. It was amazing to learn more about the theory behind the decisions made when designing OpenDP and a lot of the DP infrastructure that I'm interacting with. Yeah, we can switch to a quick Q&A session. So we have one question in the chat, and Andrew maybe has his own curiosities. Let's proceed.
Brilliant. Tudor, you want to go ahead and share the one that was in the chat, and then we'll continue from there?
Yeah. So there is a question, how can differential privacy be applied in small clinics or community care settings? where teams need to follow regulatory or general guidelines, but don't have privacy or tech experts on the staff.
Yeah, so clearly a lot of what I presented requires some expertise, either in differential privacy or in programming languages. But I think that there are several efforts, and here I would think a bit more about companies that are trying to fill the gap exactly in that space. So try to help small communities or small entities that cannot develop people specifically to learn about how to use tool, or even like the OpenDP library. They don't have this person in-house, and they can try to use these companies to help them. Without tech expertise, I think very difficult to employ differential privacy. So some expertise is needed. There is also the opportunity, and some of people in this audience and me are working on this, of using some more AI tool to lower the bar for accessing this tool. For example, we are also experimenting on using agentic AI for writing queries, so that one can doesn't need to understand really all the detail of the query languages of, let's say, OpenDP or of some of these framework, but they can just give description. Of course, there is always the issue that you need to be able to understand if what you get back is the right thing or not. So getting away without any expertise is, I would say, is impossible, but there are several opportunities.
Brilliant. Well, I think we're a couple minutes past the hour. Marco, thank you so much. This has been really, really illuminating. And man, there's so much happening in the space that doesn't get this light of day. So thanks for taking the time to kind of lay it out for us. I really appreciate it.
Thank you very much. Thank you for having me here.
Before concluding, there is a goal of this series. One of the goals is to understand how researchers approach research in general, and particularly like well-established ones. Long story short, if they would start their PhD again tomorrow, how would they approach that? What would they do differently? What would they keep the same, and so on.
Yeah, so I tried to give this a bit in my first slide and a bit in the end. I think that one key point that I would redo over and over is collaborating with people outside of my comfort zone. That was really a changing moment for my career and my life. Before the first time I was asked if I wanted to work on differential privacy, I said, no way, I don't understand anything about probabilities. Why? My expertise will not bring anything there. But then I started and I learned a lot about probabilities and I learned a lot about privacy. And I think I also learned that I can contribute a lot to this area. So that was really a changing moment for me. And I would encourage everybody to go outside of their comfort zone and try to learn more by other people and by other areas.
Wise advice. Love it.
Love it as well. Thank you, Marco, for joining us today.
Thank you.
Pleasure.
Thank you again.
Thank you. Well, this concludes our fourth episode of our Privacy Tech Talk series. Thank you everybody on YouTube for following and for interacting with us. And see you next time. Bye bye.